morning, good afternoon, good evening, academics. My name is Andrew Liebenberg. I'm a 27-year-old hydraulic student. Good morning, good afternoon, and good evening, academics. My name is Andrew Liebenberg. I'm a 27-year-old engineering student at your university, and I'm also the owner and director of Tech Hydraulics, which is a hydraulic engineering company in Stikland in Cape Town. I'm making this video as motivation for my RPL appeal that I've put through with COVID-19 and having just had my first child. My life has gotten quite busy this year, and with having to run the company through everything that's happened with COVID-19, it's been incredibly difficult to donate time to my studies. So I felt that appealing through the RPL program to finish up my formal studies would be the way forward. I have done it in the past, but I've already achieved the minimum credit requirement to receive my diploma, my NDEMC, but I need to just pass the last few compulsory subjects in order to graduate. So I felt that the RPL program was my best way forward. So just a little bit of information about me. I started working in the hydraulic engineering field about 2014. I started working for my father's company, Liebenberg Hydraulics, and I've been learning under him. He's got a national higher diploma in mechanical engineering, and he specialized in hydraulics at Cape Tech all those years ago, and he's taught me everything I know. I've done courses through Festo, which you would have received in my RPL application, which is an internationally recognized institute for learning about pneumatics, hydraulics, mechanics, all sorts of things that offer numerous classes, of which I have done 6 now, 5 or 6, I can't recall. But I felt as though the RPL program was my best way forward. I just want to finish up my formal studies for now. I may revisit it at a later stage, but for now, my diploma will do. So this video is just a little bit of an insight into what I can do and the motivation for the subjects that I've applied for. I know it's a few, but it falls within the 50% maximum that I'm allowed to appeal for. So I'll give you a tour of my workshop. I'll show you what I can do, explain my knowledge base, my capabilities, and I hope that this motivation is sufficient. If it isn't, please feel free to get hold of me. I'm sure George Liuta will. And if you need any further motivation or evidence, but portfolios and things of the like at my company are difficult to get hands on. You know, it's private jobs for companies. I don't just want to hand out information. So I felt that this was the best way. Again, if it isn't sufficient, please feel free to let me know. Thank you. So this is one of the pieces that I thought I would use for my motivation. This is a 7-ton press that I designed and built for a plastics recycling company. They needed to take these large mounds of raw plastic, chop it into smaller pieces to put into their dicer shredder, obviously to go through the rest of the process. So the criteria I was given was 7 tons and a 750 ml throw or mouth, if you want to call it that. So using that, I used the pressure force area equation, which ties into hydraulics of machines, mechanics of machines, fluid mechanics. I calculated the pressure requirement that I needed using the force and the area, obviously, of the hydraulic cylinder, or ram, and I came out at 140 bar, and 140 bar meant that I could use a gear pump, a gear style pump. They're cheap, they're reliable, it's open loop, so it's not overly complicated. There's no load sensing or anything like that. I'll explain a little bit more about that when I go to the pump on my bench and motivate my hydraulics of machines, subjects that I'm appealing for. But they're cheap, they're reliable, they're good for about 250 bar, continuous use. We don't like to run them that high, but they can go that high. Using 140 bar, I then decided on the time that I wanted the ram to actuate at, and I discussed it with the client, and obviously taking safety into account. You obviously don't want this to move too quickly. If somebody's got their hand in the way, it's much easier to react to something moving slowly than something moving quickly. So we decided on a time, and using that, I was able to determine the flow rate of the pump, and eventually I came out at 12 cc's, which I think gave, with the area of the piston, the volume in the back, full stroke takes, it's quite quick. I think full stroke's about 15 or 18 seconds. So it's not slow, but cycle time isn't important. All those factors were taken into account, so that wasn't a problem. And then using the power in kilowatts is liters per minute times kPa, pressure in kPa over 60,000. I was able to work out that I needed a 4 kilowatt motor for the power requirements. And yeah, it was as simple as that. So that gave me the size of the motor, that gave me the size of the pump. Knowing the flow rate of the pump, the size of the pump, I was able to work out that we don't really go and use volumetric flow rate equations. I can do it if I have to, but I know that a 12 cc pump at 1400 RPM, which is motor speed, gives me 18 liters per minute. Hence I can use 3/8 hydraulic line. It's good for 350 bar, and they're good for 20 liters a minute. That's just specified on the data sheet of the line, so I don't have to do a volumetric flow equation, or I don't have to apply Bernoulli's principle to conserve energy or anything like that. I can do all of that. I don't have to. I just get the data sheet and I know what the flow rate is, so I know what size the pump is. So I don't just want to throw out a whole bunch of terms and expect you to believe me that I can do everything, but I know more than enough to apply it to this. This obviously, building something like this, it ties into the subject mechanical design 3, because I obviously had to apply fluid mechanics. I had to apply strength of materials on this C channel, which is 200 by 75. I did a 7-ton formula. I worked on the center of the fulcrum with two reaction points, which gave me a worst case scenario of, what did 7 ton? The deflection was completely negligible. It's complete overkill. So I incorporated a bit of strength of materials, and that's about it. There's guides here that I had to machine. My fitter turned and machined them for me, but I designed them. I told him what clearances I wanted. I think we eventually settled on 500s clearance. They've got DU bushes in them, and that's about it. It's incredibly simple, but I obviously had to incorporate fluid mechanics, mechanics of machines, strength of materials in order to design this. And this is a very simple representation of my abilities. So I feel that that's enough on the press. I'm going to move on to explaining something that I'm a little bit more proud of, pumps and everything that I build and test and repair. But I feel that this gives you a small insight into my abilities and my knowledge base, and I feel does motivate my claim towards being exempted from the subjects that I've appealed for. How long was that? So this is a pump that I rebuilt today. It's come in from another, call it a rival hydraulics company, but we're a little bit more specialized than they are when it comes to these pumps. This is an Eaton, model number 6422. That's just the model number. Don't ask me why it's a 6422. But I rebuilt this today. I will probably post some photos of the components laid out on my desk that I took earlier today. Excuse the quality, I just took it with my cell phone, but as you can see, there's quite a couple of internal components that go into a pump like this. There's a rotating group, there's brass-headed pistons, there's a swash plate, which is what varies as a variable displacement closed-loop pump. The swash plate is what varies the flow according to the power requirements and everything like that. So this, I feel, really ties into me appealing for the hydraulics of machines, the fluid mechanics, theory of machines, all that. I need to set bearing preloads when I put pumps like this together. It's got 2 taper roller bearings. You'll see I took a photo of the shaft. It's got 2 taper roller bearings on it. And obviously the preload on those bearings is important, otherwise the bearings won't survive. So what I typically do is I do a dry assembly where there's no internal components. I just put the shaft and the bearings and the shims and everything in, and I check the rotational force that's required to turn the front shaft. And there'll be a setting, normally in the manuals. We have the ability to check. We can use an inch-pound, almost like a torque wrench, to check what the rotational torque is, but because it's typically so low, we normally go by feel. Just come to know how it feels over the years through the experience that I've gathered. Then obviously I take everything apart again, clean everything once more, and then I put the swash bearing, swash plate, rotating group, preload springs, preload shims, O-ring seals, the usual. So yeah, I rebuilt this all by myself, and I can rebuild all the major styles of pumps for all the different brands. This is a closed loop variable displacement pump with an EPC controller, electronic proportional controller. So it has two solenoids. There we go. It's got two solenoids on its big controller here, and all that effectively does is the machine that this is bolted to has a means of knowing the load that is in the system, and it varies the pump accordingly. What it'll do is there's a big piston in here with a seal on both ends and a port on either side. So the pump will start in neutral, and the machine will swash it in whatever direction that it feels. This is normally for traction on a machine, i.e. if it swashes one way, the machine will go forward. If it swashes the other way, the machine will go in reverse. That's a closed loop. The oil stays within a closed loop in the circuit, and then typically, just so that the oil doesn't overheat, the motor will have what is called a hot oil shuttle in the back, which will vent a small amount of the flow, obviously not compromising the pressure. You can work out the differential in pressure, but it's normally very small amount of flow, which obviously vents off the hot oil, which the charge pump, which is a smaller pump in the back, makes up with cool oil from the tank. And then it varies the angle of the swash plate accordingly over this piston. It just distributes a pressure signal across, which swashes the pump. So that's effectively how the pump works. Most variable displacement pumps work on the same principle. Some only work in one direction. This works in both. So it can swash across not 180 degrees, but effectively across the neutral line. It can swash, say, 45 degrees in either direction. It's not that much, but just for argument's sake, let's say it is. And yeah, I don't know what machine it comes off of. Believe it or not, it was just brought to me for a service. I can go really in depth how this works, but effectively it's a charge pump which takes oil from the tank, puts it into the larger displacement pump. It's typically a 4-to-1 ratio between charge pump and main pump. And then this pump does work. And according to that pressure flow diagram or graph, the horsepower graph, that's how the machine is governed. So I can go into all the different means of controlling a pump. You get horsepower control, you get pressure compensated, EPC, electronic proportional control. You get mechanically actuated. There's a lot of different ways to control a pump. They'll have, some have, a pump won't, but a motor that this might run will have a dual crossover. Some have dual crossover reliefs, which are effectively a relief valve that crosses over the two work lines, so that, for example, if this machine is moving in a forward direction at a very high rate of speed with all that momentum, and then suddenly somebody pulls the lever to go in reverse, the pump obviously wants to start moving oil in the other direction, but the oil has momentum. So the dual crossover relief vents the pressure that obviously spikes in that system, allowing the machine to gently coast to a halt and then proceed to accelerate in the other direction. That's how dual crossover relief works. So from my motivation for the hydraulics and the fluid mechanics, I'm very well versed. I've been in the industry for about 8 years. I've done in-course training, which I've supplied you with the Festo certificate, but I've learned far more just working for my father and being in the field. So I don't feel as though I need to give more motivation. I can do all the formulas that are required of me, the horsepower graphs. I know how to rebuild them all. Obviously, they're all a little bit different. The Eatons, the Parkers, the Bells, the Cats, they're all slightly different, but they all operate on the same principle. I'm going to go over to my test bench now. I've got a large 55 kilowatt test bench where I test all these pumps and motors. So I'll show you how I run those tests, which also touches on, I help design it as well, and it touches on all the areas of the hydraulic side of things and the fluid mechanics, where I test efficiencies and things like that. So I'll go over to the test bench. So this is my company's hydraulic testing station. We call it the test bench. It's got a 55 kilowatt 6-pole electric motor on it, controlled by a big VSD, which with an HMI, so I can check all the variables. I can see motor torque, I can see amps being drawn, and I can set the speed of the motor. We couple the pump using different plates and everything. We couple the pump to it. It's got a very large coupling that we put between the pump and the motor, which absorbs about 5% of misalignment. And I think this is good for, I'm going to lie to you, I think this is rated at 75 kilowatts, 80 kilowatts. So a little bit of factor of safety there. So yeah, effectively it's got a 400 litre tank for the pumps to draw. It's flooded suction, so it's gravity fed into the pump. So the pump, we take that variable out. We don't want cavitation or anything to be a variable when we're testing the pumps. And then it's got the 2 work ports here. It's got a valve that we use here. Forgive the cable, the O-ring holding it up, but this is effectively how we change between testing open and closed loop pumps. Because a closed loop pump, oil has to come in one port and out the other one, and for open loop it has to go back to the tank, so that's just a diverter valve, if you want to call it that. Then this is my Parker Serviceman. This is actually the brain. This tells me the flow rate, the pressure that I'm currently, the load I'm currently putting the pump under. I vary that load using this needle valve here. It's a very large needle valve. This needle valve alone was over 100,000 rand, because it obviously is used through the Parker system. And that's effectively how I test the pumps. I will couple the pump up, I will run it up to an RPM that I deem fair. It's typically about 1,000 or 1,200 RPM. I have a safety screen over there. And I run my tests. I check the control, I check the efficiency, so I'll see what the flow rate is at 0 load, and I will load it to maximum load, and I will take a percentage difference across the two, and I don't let anything leave if it's less than 90% efficient. No pump that I've ever tested has been 100% efficient. Even if the maths tells me so, it's impossible. So I don't let anything leave that's less than 90%. I've got some headland flow indicators here, so I can check things like case drain leakages, which will tell me if there's some sort of issue within the pump. So this is my means of testing. Obviously, I had to design and build this. My father obviously was the main man behind it, but I obviously know how the whole thing works. I could rebuild it again if I had to. So just to elaborate on how I feel that this motivates my claim for fluid mechanics and hydraulics of machines specifically. Yes, having designed and built this with the sliders and all the clearances and tolerances ties into theory of machines, ties into mechanics of machines and mechanical engineering design and strength of materials, and there was a lot of formulas and a lot of math that went into designing it, but it was so long ago I wouldn't be able to tell you any of it. But I feel that this is more of a motivation for the hydraulics and the fluid mechanics specifically. The efficiency tests I run, the way that the pumps are controlled, the horsepower ones specifically, they have a peak horsepower curve. They are typically run on diesel engines. So the diesel engine only has so much power to give. So I will take the flow rate of the pump and the maximum working pressure. I will use those two to work out the power draw, and then I need to know what to set that power draw to. There are DA controlled pumps, there are DFLRs. I can throw out a whole bunch of terms, but effectively it's just different means of controlling the pump. And they all need to be set, and I know how to set all of them. I don't have a pump on the test bench to demonstrate to you. If that's something you would like to see, I have to test that pump in the next day or so. I will probably shoot a video thereof. I just shoot efficiency videos for my clients. I don't show them the whole controlling of it because they don't need to know, and frankly they're not interested. They just want to know that it's right. So I feel that this is my main motivation for my hydraulics of machines and everything. Like I said, I know the difference between closed and open loop pumps. You get gear pumps, piston pumps, variable, fixed displacement, bent axis, all the different mountings, all the different sizes of fittings, the different flow rates the fittings can handle, the different types of pipes, the pressure ratings, the flow rate requirements, or the flow rate specifications of the pipes. I know everything. I don't know everything, but I'm fairly well versed in hydraulics. So I really do feel that I'm worthy of being granted the credit for the subject. It's not something I feel like I need to study further in. I'm learning about it every day, and I learn every day. Not a day goes by that I don't discover a new way to do something or have a new challenge put to me. In my RPL application, I mentioned HPV 9595, which was a really difficult pump that I had where I just could not get the efficiency out of it. And we started removing controllers and bypassing circuits, and just to figure out where the problem was. And at the end of the day, we found out that it was such a small thing, just a small component that was out of spec, and we ordered the new one, and the efficiency came up. It wasn't perfect, but the efficiency came up to a point where I was happy to send it. So yeah, that's about everything in a nutshell. Obviously, it's just some gauges so I can check various things, casing pressures so that I don't blow the seals out of the pumps and things like that. I've got a small power pack mounted underneath the tank if I need to use pilot signals. Some pumps need pilot signals in order to swash 30 bar, 24 bar pilot signal. I set charge pressures here, I set maximum working pressures, I set bypass valves. There are many valves, there are many pumps, and there are many ways to control them all. And I'm fairly, and like I said, I won't repeat myself again, but I'm fairly well versed in all of them. So if you require additional information or an example, I can run a test. I can send it through to you with the greatest of pleasure. It will be quite long. The tests do typically take between half an hour and 45 minutes, depending on how in depth they are, but I can show you a simple one if you'd like with a gear pump. Just let me know. Thank you for your time. So I thought I would just shoot a quick little glimpse into how I operate this machine. Like I said, I don't have a pump on it at the moment, but I don't want you to just take my word for it. So here's the serviceman currently on. I'll just keep the light on. I'll supply you with a close-up view, but effectively there's pressure, flow rate, and temperature. The motivation that I can give for the thermodynamics 2, I passed the practical. I didn't pass the theory. I was able to apply the theories I'd learned, dryness fraction of steam and fraction of steam and all that, and the chemical tables and all that. I was able to apply that, and I passed the theory, passed the practical. I don't know why I didn't pass the theory at the time. I did it quite a long time ago. I think it was 2018 or 2017. It was quite a while ago. I don't have much motivation for that. We do send oil samples away to get tested, so I do understand how the viscosity is affected by temperature. I do understand lubricity. That's the only application I have in my field of work that may tie into thermodynamics. Effectively, we know what the optimal working range is of hydraulic oil. It's between 45 and 65 degrees. That's the optimal working range. It can go higher, but effectively anything past 80 degrees and it starts to lose lubricity and it starts to come apart. But I understand viscosity. I understand the Setty-Stokes, the unit of measurement. I understand lubricity. That's all I can really apply to thermodynamics. But back onto this, effectively this will give me my flow rate. I can load it using my needle valve here. I can load the pump, I can check efficiencies. This will tell me if there's cavitation, if the horsepower curve is set too high or too low. I come to my HMI here, so I'll start the motor for you. So I'll just run it loose. That's 500 RPM. So that's how I will effectively run the pump. Then I will be getting a reading here. I'm just going to switch the computer off to say battery. And then I can see how much torque the motor is producing, what current it's using, the current RPM. We went for a 6-pole motor, which is only 990 RPM, but it has a more stable torque curve at lower RPM. So a typical 4-pole, which is a 1400 RPM motor, the torque curve tends to drop off below a certain RPM and above a certain RPM, and because I need to spin pumps as slowly as 650 RPM, that the 6-pole motor was the way to go. And effectively this is how I run my test. I've got all the information I need to go and to plot graphs for my clients, to go and plot power curves, efficiency curves, relay those to the manuals to see if everything correlates correctly, set DA pressures, charge pressures, that all I'll check here with my other loose gauges. So this is effectively how I run a test. I'll just stop the motor there. This is how I run my tests. I can also test motors where we use the motor, the electric motor, as a brake. So I'll turn it over into motor mode and mount a hydraulic motor here and run that off of a separate hydraulic power unit, power pack. Spin the hydraulic motor, and then I will load it incrementally with a percentage of this motor's torque as a brake. That will also allow me to check how we check the hydraulic motors. We'll check the hot oil shuttle, like I mentioned previously in the video, where the flow rate of that needs to be set so that you don't lose too much of your workflow. Those I check with the headland flow indicators here. So I'll set that, that's a setting I have. I can check crossover reliefs, obviously spin it in the one direction, then immediately spin it in the other to check that those are set properly. Always set it a little bit above maximum operating pressure. So just for those spikes, so that it never comes into play while the machine is actually operating. It's just for those big spikes in the circuit. And then this is a big braking resistor which sheds off when this electric motor is being spun by the hydraulic motor. It effectively becomes a generator, and I can't feed all that power back into the VST. The VST can't handle it. So the big bug zapper on the wall is a braking resistor. It just sheds off that generated power as heat. It's way over-spec'd for what we need. Everything I do here, I go over. My factor of safety is high. Like I say, if I do a calculation, a strength calculation for a press or a cylinder that I design and build, I design and build hydraulic cylinders as well. I make sure that the shaft diameter is far above the minimum requirements for the slenderness ratio. I make sure that the wall thickness is far higher than it needs to be. The clearances between bushes I make sure aren't loose but are bigger to prevent galling of the materials and picking up, because obviously a lot of dirt and stuff gets into these systems. So if the tolerances are too fine, the dirt does more damage than if the dirt gets in. So that's effectively how I would run a test on the test bench. It's got a lot of components to it. There's quite a bit of calculations that need doing, but it's all the same stuff that I do over and over and over again every day. So once again, I feel like a parrot, but I'm quite well versed in how to do it. I've been doing it for a long time now, and I feel that this is pretty sufficient for my motivation for hydraulics anyway, my hydraulics stream, but fluid mechanics as well. I understand all the principles and I can apply them to the hydraulic trade. I don't need to do energy conservation formulas day to day. Bernoulli's equation and things like that. I don't need to apply that on a day-to-day basis. But if I had to work out the pressure differential across a valve, I could. If I had to work out, I don't know what other examples to give. Heat generation through an orifice, I could, but I don't need to. So effectively, yeah, that's how I run my tests, and I'm just going to ramble now, so thank you for your time. Okay, charge pressure is 21 bar. See the pumps on test. No leaks. No leaks. No leaks. That was just from when we tightened the pipe here, so no leaks. Nothing coming out from underneath the controller here. Nothing coming out the sides. Nothing coming out here. So no leaks. Currently got it on the front solenoid. Like I said, no leaks, nothing out the front here, no leaks out the front. Pump's like new, 37, 38 degrees. Pump's good. I apologize for the noise, but here's that 6422 on test. So this is the suction line. Here are the main work lines going into my test bench. As you can see, I've just got it under a slight load just to generate some heat, get the viscosity to the right spot, we don't like to test them cold because that can give a false reading. As you can see, I think it's 750 RPM. Yeah, 750 RPM, and that's good for 80 liters a minute. So, yeah, there's probably about 100 liter pump, 100 liters a minute. Charge pump is staying cool enough. This is the case drain line, which vents off any leakages internally so that the front seal doesn't blow or any other seals blow out. And yeah, this is running in a closed loop. That's why that valve is closed currently, so the oil is just circulating through. And then the electronic solenoids here, I've got them on a 24 volt power supply or variable power supply, and I can swatch this pump in either direction that I choose. And then the main relief valves, these are the two main relief valves here and here. They're obviously set to maximum working pressure. I think they're a combination valve as well. They what we call like a high pressure cutoff. So effectively, if the machine works, if the pressure goes too high, you don't want it blowing off against the relief valve for minutes and minutes on end. It'll generate a lot of heat. So if it gets past a certain pressure, it actually de-strokes the pump. It sends a signal back to the controller and it'll de-stroke the pump instead of the pump staying in full swash and blowing off against the relief valve. So this is effectively how a test is run. I just couple it up with an adapter, one of those adapters, and I test it. The charge pressure is right at about 19 bar. It's not very high on this pump, and I vary this needle valve to load the machine, and I can let it run at all various loads. I can take the pressure and the flow and plot a horsepower curve for the graph, which I give to my clients.